Hello, my dear students, and welcome to this bonus video about Simpson's rule. It's something that we cover briefly in class, and while the standard material is more than enough to solve real-world problems, I wanted to make this video as an additional resource for you, in full detail about why Simpson's rule works. First, let's briefly review what Simpson's rule is. Just like the left endpoint method, the right endpoint method, the midpoint method, and the trapezoidal rule, it's a way to use the interpretation of an integral as an area to approximate integrals by subdividing that area into smaller pieces. In the case of the trapezoid rule, those pieces are trapezoids. In the case of Simpson's rule, those pieces are areas under quadratic polynomials, or segments of parabolas. One big difference is that to fix a linear function, like we do for these trapezoids, we only need 2 points. To fix a quadratic function in space, we need 3 points. This is why Simpson's rule uses sets of 2 delta x's, or little changes in x, per quadratic function. Just like the other methods, the approximation usually improves as delta x decreases to 0. This method is particularly good for sinusoidal functions, and of course, just like the trapezoidal method is exact for linear functions, Simpson's rule is exact for quadratic functions. As you can see here, the function is being fit to approximating parabolas, and the area underneath those curves is meant to approximate the area under the function itself. These approximations get better and better as delta x decreases, or in other words, as the number of subintervals increases. Note that we need to use equally spaced input points for this method, so delta x is consistent. We'll see why later. Another connection we'll need is to recall that the average value of a function over an interval is defined like so. The consequence of being able to find the average value of a function over an interval is that the corresponding area under the curve on the same interval can now be represented as the length of the interval times that average value. It's the area of a rectangle. Here's an example of Simpson's rule applied to sine of x, with delta x equals 1.5. There are 2 approximating parabolas between x equals 0 and x equals 6, split at x equals 3. So we get these 2 areas we want to add together to approximate the area under the sine curve between 0 and 6. We can use the average values of these functions now to make these convenient rectangles with the same area. So we're still estimating the area under the sine curve between x equals 0 and 6 using quadratic approximations. Now, as you can see, the area of these rectangles is going to be 2 delta x, which is 2 times 1.5, or 3 in this case, times the heights of these rectangles. But the height of each rectangle is the average value of the quadratic function, fitting each set of 3 points. I'm going to label these points so you're ready for the next part. Here we go. We're going to use one last technical piece of information to get Simpson's rule, and this is not obvious, so I'm going to show all the steps at the end of this video. The statement is the following. For a quadratic function p of x, fitting equally spaced points along x, xi in its output, xi plus 1 in its output, and xi plus 2 in its output. The average value of this function from xi to xi plus 2 is exactly the y value of the first point plus 4 times the y value of the second point plus the y value of the third point, all over 6. What this means for us is that the height of the blue rectangle using I equals 0 is f of x0 plus 4f of x1 plus f of x2 all over 6. And the height of the purple rectangle using I equals 2 is f of x2 plus 4f of x3 plus f of x4 all over 6. This means that our approximated area is the following. We can factor out the 2 delta x and the 6 since they're in all the terms. 2 divided by 6 is 1/3, so we're left with delta x over 3 on the outside. Notice that all parabolas contribute both their endpoints. So when we add these subareas together, all the outputs of even indexed endpoints that aren't also endpoints of the entire interval, like f of x2 here, need to be double counted for a factor of 2. This leads us to the general formula for Simpson's rule. The formula is delta x over 3 times a bunch of f of xi's where the coefficients inside the brackets are 1 for x0 and xn, the first and last x values, 2 for every other even indexed x value like x2, x4, and so on, and 4 for every other term. Note that the chosen n must be even for Simpson's rule to be defined, otherwise we wouldn't have a full parabola at the end. Fun fact, there are other versions of Simpson's rule, which is why this formula is sometimes called Simpson's 1/3 rule, because of the 1/3 which is multiplied into every term. Let's solve the problem together. We wanted to approximate the area under the sine curve between 0 and 6 using Simpson's rule with delta x equals 1.5. Since the interval starts at 0, x0 equals 0. Then x1 equals 0 plus delta x, which is 1.5. x2 equals 0 plus 2 delta x, which is 3. x3 equals 4.5, and x4 equals 6, the other endpoint. The function is sine, so f of x1 is f of 1.5, which is sine of 1.5, for example. Using Simpson's rule, we just have x0 through x4, so the coefficient of f of x4 is just 1. All the other coefficients can be read directly. We know what all these values are. We know f of x0 through f of x4 because those are just the outputs of the sine function. We also know delta x is 1.5. Putting everything in, we get this, which evaluates to a slightly positive number, which should make sense after all, because the integral of sine from 0 to 2 pi, which is a little more than 6, is 0, because the areas cancel each other out. So if we exclude the area between x equals 6 to 2 pi, which is only negative, we're left with a little positive number. How delightful! The real answer is different, naturally, since we chose such a large delta x, but it's still quite impressive for just 5 points. It's pleasant to note that the midpoint method is also good for this specific question, and I encourage you to think about why. You may be asking, if we can find the real answer, why do any of this? And that's a great question. Some real-life integrals are quite tricky to solve, and notice that in all these methods we don't find any antiderivative at all. We just plug in the output values of the original function, and those are almost always much easier to find. Now, we used this technical result but didn't prove it yet, so I wanted to share that with you before concluding this video. Let's say we have a quadratic function p of x that fits these 3 points, xi, xi plus 1, and xi plus 2. Any quadratic function has this general form, and it turns out this is enough for us. From the second statement of the result, we can extract this equation. The left-hand side comes from the average value formula applied to this quadratic function from xi to xi plus 2. The right-hand side remains unchanged. Let's work with the right-hand side first. Notice we can use either p or f here because the quadratic function p is exactly fitting the true function f at those points. We know more about p, so we'll use those outputs here. Use the general formula of p of x to find f of xi plus 1, and f of xi plus 2. We get these equations, changing all the x's to their new indexed values. Plugging these in, we get this slightly longer equation. Keeping what we had but adding space, and rearranging by putting the a's, b's, and c's together, we know that the right-hand side is equal to this nice expression. For example, we had the terms a xi squared and 4a xi plus 1 squared and a xi plus 2 squared. All of them have an a, so we regroup them in this way. Now, we're going to use that the points are equally spaced, because this tells us that the x point in the middle is the average of the 2 points around it. We put in the points, and now we can simplify nicely. This is exactly what we had before. Let's evaluate this square, recalling that the square of a fraction is the fraction of the squares. Then I use the sum of squares formula, and 2 squared is 4. We're multiplying that squared term by 4 to begin with, remember? So that 4 is going to cancel out. Then we are left with, on the inside of the term multiplied by a much nicer 2xi squared plus 2xi xi plus 2 plus 2xi plus 2 squared. There we go! For this next one, it's a little easier. 4 divided by 2 is 2, so the term just becomes 2xi plus 2xi plus 2, which gives us 3 of each in total. Then 1 plus 4 plus 1 is 6. Rewriting, factoring out a 2 and a 3, and then splitting up the fraction gives us this nice result. So we know the right-hand side is equal to this. Just putting that up there where it goes, how cute. This is enough work on the right-hand side. Let's work on the left-hand side and see what we can get. First, we have an integral of a quadratic, so we'll use the reverse power rule here to get an antiderivative. These coefficients have some nice foreshadowing. See if you can spot it. Evaluating the endpoints using the fundamental theorem of calculus, and then combining terms of a, b, and c like before. And we're on to something. I think we should use the difference of cubes formula and the difference of squares formula. I'll put them up as a reminder. Using these formulas, we get the following. This might look like a lot, but guess who's everywhere? It's that term xi plus 2 minus xi. Let's cancel those everywhere. Both sides have been shown to be equal using only the assumptions given. So the statement we were proving is indeed true. Thank you for watching, and I hope you have a great day.